Log on, tune in, find out. Another good idea from Cambridge.
Set up yet a proper chairman system, so I have to introduce myself. So I will give 3 lectures about Hecke algebras at roots of unity. I guess these Hecke algebras will show up at several places in this program. Today's lecture is something like a motivation why we are interested in Hecke algebras at roots of unity, and this comes from the representation theory of finite groups of Lie type. So in this one lecture I want to kind of survey the situation there. We will not go into too many technical details. This would really be another course otherwise, and then from tomorrow on we will just speak about the Hecke algebras in the proper sense. So I want to consider a finite group G which is not just any finite group, but a finite group which arises from an underlying algebraic group by taking fixed points in a finite field. So this G underlined should be a connected reductive group, algebraic group over an algebraic closure of a finite field. So Q is just the prime power here. So this FQ is the finite field. And by this we mean that we assume that there is an FQ rational structure on this algebraic group, and we take coordinates in the field with Q elements. So if you are not very familiar with this, just think of the example where G is GLN over FQ bar, and then you can define a Frobenius map which sends a matrix to the matrix where you raise every entry to its qth power, and then if you take fixed points under this map, which means you take just matrices whose coordinates are in FQ, you get the finite general linear group. Yeah, so as I say, if you don't know the general setup, just think of this example and you will already see non-trivial problems and questions just in this example. For those who know what connected reductive groups are, I don't have to say anything more here. Yeah? So what we want to do is to study, or eventually to understand, the irreducible representations of all these finite groups. Yeah? So that's the big aim in the background. So suppose K is an algebraically closed field. Any for the time being. Yeah? So we want to understand this problem for any algebraically closed field. Yeah? So by understanding, of course, there are several levels of what you would want to know about this. For example, you would like to have a nice classification. Somehow an indexing of the irreducible representations by some nice natural set. You will certainly want to know dimension formulas Yeah, ideally, some formula which expresses this dimension here in terms of this nice labeling. And of course, you can ask more refined questions about character values and such things. Yeah? You want to be able to compute such traces for arbitrary elements in your finite group. Now, as your question already indicates, it is very likely that this problem will look different according to the characteristic of this field K. So there are three major cases. If this here is 0, or if next case would be that the characteristic of this field is the same as the characteristic over which the group is defined. And the third case would be that it's again positive characteristic, but not the same. So we have these three basic cases. Yeah? Now, this here is, of course, the best known case because it's well known, a finite group over a field of characteristic 0. Well, the representations of a finite group over a characteristic 0 is the classical representation theory as invented by Frobenius. Everything is semi-simple, let's say. So this is equivalent to finding the character table of this group. Yeah? So this is the best known case. And the big open problems, let's say, reside really in these two cases here. Now, how do Hecke algebras come into this picture? Well, when you try to attack this problem, one can split the methods that are available into two major parts. So there is an elementary approach which one can carry along a certain way. So this basically consists of considering the induction of representations from, let's say, natural subgroups which come with such an algebraic group like Borel subgroups or parabolic subgroups. And then, as I said, so this approach, it is possible to carry it a certain way, but then one really has to use more heavy stuff. So that's algebraic geometry, or this theory of perverse sheaves, which showed up in Pramod's talk, which leads to the most decisive results here. So the basic idea of this second approach is really to use things about the underlying algebraic groups and the geometry that comes from there, while this first approach doesn't really use the algebraic group structure. You just stay within the framework of the finite group. Now, what I want to do in my talk here, at least today and probably tomorrow, is just to stay within this elementary approach, and then maybe we will see later anyway, as Pramod's course goes along, he will mention applications to representation theory, and maybe next week anyway in some other courses we will see more about how the algebraic geometry comes into this picture here. So for these talks here, we will stay mainly with this first approach. So this one, and if we take somehow, what is the purpose here in my talks? I said I don't want to go into too much detail. So if we take a very broad view of this, then this approach here relies very much on the following idea. It's based on using certain Hom functors. So I just want to explain a fundamental result here. And this can be explained actually in some more general terms. So let's assume that A is a finite dimensional associative algebra over K, M a finite dimensional A module. So I don't make any assumption on this M, it will not be simple in general. So in order to study its structure, I look at its endomorphism ring. So let's call this E. That's again an associative algebra. Actually, it will be more useful to look at the opposite algebra of this. So in this very general setting, we can always set up the following functor. So we look at left A modules, and we can go from these left A modules to left E modules. By a very natural procedure. Namely, if we take a module for the algebra A, then I simply take Hom A M V, and this becomes an E module. Yeah? See this? Yeah, if you have a homomorphism from M into V, and you take an endomorphism of M, you can just compose with this. So if phi is in E, and you get another element of Hom M V. Yeah? So in this way, this E acts on this Hom space just by composition with of maps. Yeah? So E acts on Hom via, so phi dot F is just this composition here, composed with phi. And this is why I take, or have to take, the opposite algebra here, that it comes out right, that I really get a left action here. Otherwise I should, if you don't like to use the opposite algebra, then you have to take right modules. Huh? So it's a question of what you prefer. If you just want to stay within left modules, you have to pay this little price here. So this is a very general thing, of course, and it's somehow surprising that one can say something non-trivial there at all. And this is the following result, which really is at the heart of these applications of Hecke algebras. So this goes back to its first versions to J.A. Green from about 78, but it was formulated in a more special situation, and then the most general versions are due to Caban, Linkelmann from the 1990s, and probably some other people. So we have to make two basic assumptions to get some result here. The first is the following. I need to assume something about this module M. I said I don't assume it's simple or even semi-simple, but I have to assume something about its composition factors. And the precise assumption is the set of composition factors of the socle of M, so all simple submodules of M, that this set is the same as the set of composition factors of the head of M modulo. So whenever a simple module is a submodule of this M, it should also occur as a quotient module and vice versa. I don't assume that the multiplicities are also the same. It's just the sets should be the same. So this is one assumption. And the second assumption is something about this algebra E. So this algebra E should be symmetric. Or it's actually something more general is enough. More generally self-injective. So self-injective means that every projective module is also injective and vice versa. Yeah, so the notions of projective and injective are equivalent. And under these two assumptions, one can say something interesting about this functor. Namely, then this functor f produces a bijection between all simple A modules which occur in this set. So V occurs in A, so either in the head or in the socle of this module, and up to isomorphism here, and the irreducible representations of E. And this is simply done by this functor here. Yeah? So under these relatively general and mild-looking conditions, this functor gives us really a bijection between these sets of simple modules. Yeah? So that's the very general result. It's not so hard to prove it. It's a general result about representations of finite dimensional associative algebras. So let's see two situations where we apply this, and this will then show how this theory of Hecke algebras comes about. So the first situation is actually the classical situation considered by Green. So this is Green, but already Green did not start this. This was merely already some kind of endpoint of this development. So other names to mention here are Zawada, Tinberg, Curtis, and Rischen. So we assume that we are in this case where the characteristic of K is the same as the characteristic over which the group is defined. We consider a Borel subgroup. So in our finite group. So we know that this has a semi-direct product decomposition, where this is the unipotent radical. And actually here, so here I mean really all these things in the finite group. So this unipotent radical here is the CeLO P subgroup of G. Well, if we consider irreducible representations of a P group over a field of characteristic P, we know the irreducible representations there, it's just a trivial representation. So let's denote this by this. This is the trivial U module. And actually, easy consequence of this is that if you consider any irreducible representation of G, and if you restrict it down to this U, so we restrict it to U, will have this trivial module as a quotient and as a submodule. Yeah? Has a submodule and a factor module. And so by Frobenius reciprocity, we know that V is a submodule and a factor module of the induced representation in U from G Ku. Yeah, so we are somehow entering a situation where this condition A here is actually satisfied for all simple modules when we take this module here to be M. Yeah, so this motivates to, or let's see what happens if we take M to be, so to place ourselves in this setting. So let A be the group algebra of G and M this induced representation. Then this condition A is satisfied where these sets consist of all irreducible representations of G. Yeah, so then A is satisfied where the sets consist of all of the irreducible representations of G. Yeah. Now, furthermore, if we want to apply this theorem, we need to know something about the endomorphism algebra of this module M. So E now this here is an induced representation from a trivial separate representation of a subgroup. So there is much known about such endomorphism rings. This is a permutation module. So this is already due to Schur, I guess. Such a thing as what is called the Schur basis. You can write down a distinguished basis for this algebra. You can express the multiplication of two basis elements in terms of intersections and conjugates of this subgroup. So everything, so the structure of this algebra can be quite explicitly described here. So I will not write down the actual formulas here, but you can obtain actually an explicit presentation of E in terms of generators and relations. And then actually it's not so hard to classify the irreducible representations of this. You can find that so actually they are all one-dimensional. Yeah? Yeah, in this case, all the irreducible representations of this endomorphism ring are one-dimensional, and there's a nice way of indexing them. So applying this theorem then gives us, so the theorem, I should also say then, since you can describe this structure quite explicitly, you can also check that E is self-injective. So everything, this theorem applies, and this theorem tells us then that the irreducible representations of G, this was, this theorem says something about this functor, about the set of all irreducible representations of A which satisfy this condition. We saw that actually this is all of ir A here. So this theorem tells us that we get a nice parametrization of the set of irreducible representations of G in terms of the irreducible representations of this endomorphism ring. Yeah, this was one of the classical applications of this this Hom functor idea. So this is how far as you can get with this elementary approach. So for example, Curtis, he used this to reprove an old result of Steinberg's, namely that if G is simple and simply connected, then by just looking at the indexing set for the irreducible representations here, you find that the number of irreducible representations here is Q to the rank of G, which is an old result of Steinberg's, which you can prove then in this elementary way. As I said, this is how far you can get by just these methods. If you want to know more, like dimensions of irreducible representations here, there things become more complicated. So the best what is known here is if P is large, then you have Lustig's formula for the dimensions of these irreducible representations. But this doesn't seem to be possible to attack such questions from these elementary methods. Okay. So that's this classical situation. Now let's look at the other case, namely that the characteristic of K, let's call it L, and actually it works in both cases when L is 0 or L is positive, but L should not equal to P. Well, the first observation is that in these cases the above argument does not work. Well, unfortunately I wiped it out here. I mean, the starting point of this discussion was the fact that the irreducible representations of this U, the unipotent radical, over a field of characteristic P just consists of the trivial representation, and this simply isn't true if we don't have this condition. So from the start the whole argument breaks down. So or otherwise put, there exist irreducible representations of G such that V restricted to U does not contain the trivial representation of U. So what you do instead here, you have to consider more general types of modules and inductions. So you consider parabolic subgroups. So such a parabolic subgroup has a Levy decomposition, and using this decomposition you define two functors, RLG, which goes from KL mod to KG mod. So this is called Harish-Chandra induction. And the other way around, RLG star from KG mod down to KL mod. So that's Harish-Chandra restriction. So how are these defined? So if you start with a KL module, you can regard it as a KP module. So let's denote it by V tilde. Yeah, so you know L is a factor group of P, so you can just inflate the action from L to P by letting this act trivially. Yeah? So UP and then you induce from here to G. So RLG of V is int from P. Yeah. Of course you could have induced directly from L, but you gain a little bit by first going to P and then inducing. Yeah. So the induced thing will be smaller. And to go down from KG to KL, so if you have a KG module, then you observe that by taking the fixed points, yeah, so you take all vectors in V which are fixed by all elements of UP. And since UP is a normal subgroup in P, i.e. it's normalized by L, you easily check that this is an KL module. So in this way you can define these two functors. There are of course a number of questions here to ask. For example, I don't carry this P in the notation for these functors here, and this is a non-trivial question to show that this does not depend on P. Yeah, the same levy could be a levy in non-conjugate parabolic subgroups, and then there's a real question if these two functors are the same. But these things have all been solved by now. Of course, they had long been known in characteristic 0, where everything is semi-simple anyway, and then it's a character computation. But in positive characteristic, where modules are not semi-simple, you really have to prove something about these functors. And this was done by Dipper and Du and by Howlett and Lehrer in the 90s. So we have these functors. Well, also they satisfy analogous properties as usual induction and restriction. You have transitivity, you have a Mackey formula, such things. And then comes the basic definition here. So an irreducible representation of G is called cuspidal if whenever you restrict it to a proper levy, you don't see it anymore. Yeah? For all proper levy subgroups of G. Yeah? So what you then, using this concept, you obtain a partition of the set of all irreducible representations of G. So given, should say here, so this is the definition of what it means for an irreducible representation of G to be cuspidal. The same definition then applies to every levy, because every levy is again such a group G here. Yeah? So same definition. Applies to since every levy is again such a finite group of Lie type, of this type here. And then what you do is the following. So consider pairs Lx, where L is a levy of some parabolic subgroup of G. And X is a cuspidal representation of L. And then you define say this piece of the set of irreducible representations of G to be all Y in all irreducible representations of G such that X is a composition factor of RLGY. Yeah? So given such a pair, I single out a certain set of irreducible representations of G, namely those which somehow can see this X here when I restrict down to L. And with this definition, one can then show that we get a partition of this set. So, and so the pieces in this partition are indexed by all these pairs, but of course modulo some modulo conjugation inside the whole group. We have this here. Yeah? So and this is then called the Harish-Chandra series above Lx. And you see in this way, well, what I want to say here, what I want to point out is that this uniformly works with these assumptions. It works in characteristic 0, which was long known already in the 60s, well, in the 70s probably, the last century. But it also works in positive characteristic as long as this positive characteristic is not equal to p. These results are a bit more recent, so they date from the 80s and 90s. So first this was done appeared in the work of Dipper and James from GLN, and then it was generalized to other types by Dipper, Du, His, Malle, and myself. But what is somehow nice in the end, that also really the proofs, everything just works uniformly under this conditions there. You don't have to distinguish in the proofs between characteristic 0 or positive characteristic. Now, once we are here, we have again a situation where this first general result about Hom functors applies, namely, so we fix now Lx and set M to be this Harish-Chandra induction. Of course, A, the group algebra of G. And then, well, there is an endomorphism ring associated to this. And the question, are these conditions again satisfied? Do we have bijection between these pieces and these endomorphism rings? So for this, we have to check these two conditions, A and B. So what was A? A was saying that every simple module, which is a factor module of this, is also a submodule and vice versa. So this is of course true in characteristic 0, because everything is semi-simple. Everything which is a submodule is a quotient module. So this is in characteristic 0. This is obvious, since M is semi-simple. So here in positive characteristic, you really have to prove something. And this was first done by His, so it dates from the 1990s. So this is true. And then we had the second condition about the endomorphism ring. So what was B? It said that in the most general version that this E should be self-injective. But even something stronger is true here, that this E is a symmetric algebra. It's stronger than self-injective. So symmetric means there exists a trace form, trace map. So just a linear map such that tau of AB is tau of BA, which is non-degenerate, such that the associated bilinear form so we define AB to be tau of AB is non-degenerate. And this again, this was this was first shown in characteristic 0 by Howlett and Lehrer. Namely, what Howlett and Lehrer did was to find actually a presentation of this algebra in terms of generators and relations. And once you have this presentation, you can simply write down such a trace map here. And again, in positive characteristics, something had to be proved here, and for this, so this is where I also have a contribution here. So this was done by his Malle and myself. We simply showed that this whole Howlett-Lehrer theory simply goes through in this case. Yeah? You have to rearrange a bit their original proof, but essentially everything goes through what they did in characteristic 0. So what this means then is that we can apply our Hom-Functor theorem, this theorem Green-Caban-Linkelmann. So, and what this tells us is so the Hom-Functor theorem implies, so it established a bijection. Oh, it's not written anymore. So what was it? It was all irreducible representations of A. No. Such that this irreducible representation occurs in this set of composition factors of the head or the socle, and the irreducible representations of this endomorphism algebra. So in the current situation, this amounts to the following. So in the present situation, so here we have the irreducible representations of this endomorphism ring. And this set here, so the set of all irreducible representations of G, which occur in the head or the socle of this M, of this Harish-Chandra-induced thing, but by Frobenius reciprocity, this is the same as considering all irreducible representations of G, whose Harish-Chandra restriction contains this X. So it's actually exactly this set here. Yeah. Yeah, so this finally, you see the result, the end result is very roughly the same as in this previous case. In the first case where we had this same characteristic situation, we just had to consider one module M and its endomorphism ring, and already all irreducible representations of G were in bijection with the irreducible representations of this endomorphism ring. The situation is not as simple in this case. Here we first have to cut this big set into these pieces indexed by these cuspital representations of Levy subgroups, but then each such piece is again in bijection with the irreducible representations of such an endomorphism algebra. So now eventually you have two problems to solve to understand your irreducible representations. Well, the first is we have to know what are the pieces in this partition. So you have to know the cuspital representations of all levies. Yeah? So find cuspital representations of L, of all levies of G. And secondly, determine the irreducible representations of such endomorphism algebras. Yeah. Well, and this is such, these algebras are what we would typically call Hecke algebras. Yeah? So here the situation is such that in characteristic 0, these two problems are basically solved. So the classification of Caspital representations is due to Lustig in his work on characters of reductive groups over finite fields. So in the end you have a complete classification of all Caspital representations. And again, this is not at all elementary. You will need to use this theory of perverse sheaves again here. And in the second problem about these Hecke algebras, well, this is also solved by the results of Howlett-Lehrer plus Tietz deformation argument. This implies that the irreducible representations of this algebra, well, you see we are in characteristic 0. This is semi-simple. The endomorphism ring of a semi-simple representation is again a semi-simple algebra. And so actually this here is just in bijection with the irreducible representation of a certain finite group. Let's call it WLX, where WLX is the stabilizer of X in NGL mod L. Yeah? So X is a representation of L. You look at the normalizer of L, and you look at the subquotient of this, which stabilizes this X. So this gives a certain finite group, and actually the irreducible representation of this algebra are just in bijection with the irreducible representations of this finite group. And actually, in most cases, not all, this is close to a finite Coxeter group. In most cases, whatever this means. For example, if this G underlined here is a connected reductive group whose center is connected, then this is always a Coxeter group, just a finite Coxeter group. So I guess we arrive here at a point where we can almost stop for today. So the real issue nowadays is to try to understand the case where we are in positive characteristic. Representations are not semi-simple. We cannot, or it's not yet known how one could possibly extend Lustig's method to the positive characteristic case. So already this first problem, so classification of Caspitals is open. The only known results here, or the best known results here, are in GLN. So this is the work of Dipper and James in the 1980s and 90s. So what the special feature of GLN is in this context is that every Caspital representation in characteristic, in positive characteristic, lifts to a Caspital representation in characteristic 0. And of course the L modular reduction of a cuspital representation in characteristic 0 is a cuspital representation in positive characteristic. So here we know all cuspital representations in positive characteristic, and the classification is the same as in characteristic 0. This is one reason why GLN, also in this positive characteristic case, is so much easier than other types of group. This is definitely wrong for any other type of group. So this is not true. So we only have very partial results for other types of group. There's one big idea missing, how to classify cuspital representations in positive characteristic. And then the second thing, this problem here, well, this argument simply breaks down. Yeah? I said, okay, one can extend in some way the Howlett-Lehrer theory from characteristic 0 to characteristic L, but its deformation argument is about semi-simple algebras. So there's no way that one can use this here. Huh? So this is in general is non-semi-simple. So its deformation argument cannot be applied. So we would like to know how to classify the irreducible representations of these non-semi-simple Hecke algebras. And this is somehow the idea of what I want to do in the remaining talks. So what we will see is, so we will see so there exists at least a natural injection of this set into the same set as there. So we still have this, this, let's call it inertia group of this cuspital representation here. So they are there independently of any characteristic. And in general, we cannot expect that we have a bijection between these two, but at least we can find a natural way of injecting this here, and in this way we get the classification of these irreducible representations here. So this is what I want to explain in the remaining talks. So for those who have seen this already a bit, think of the example of GLN. In the simplest case, for example, this endomorphism algebra here is a Hecke algebra of type A. This group will be the symmetric group Sn. So these irreducible representations are labeled by partitions of n. In the modular situation, you would have to use something like L regular partitions to label the irreducible representations here. So there you have a kind of embedding L regular partitions embedded in the set of all partitions of n. So in a sense, this result here is a generalization of this idea of L regular partitions embedded into all partitions of n to all types of groups and all situations here. So for this we have to develop some general machinery, and this we will do then tomorrow until Wednesday. Okay. Okay, so are there any questions or remarks? I think then we have a break until 2 o'clock, where we go on with Joe Chuang's talks. Okay.